The next two instructions we'll support are the load and store word instructions, and we'll need to add the data memory to our data path. The data memory takes in a 32-bit address input for both load word and store word, while the 32-bit data input is used only for store words. For both load word and store words, the address is the sum generated by the ALU from the contents of RS acting as the base register and the sign extended immediate, which is the address offset. Again, RT acts as the source register for load words and as a destination register for save words. We will assume that the data memory simply acts like a register file with combinational reads and sequential writes. More details on how real memories work will be discussed on the last 2 weeks of this course. To save or write into the data memory, both address and data must be provided, and the write mem signal must be asserted when the clock rising edge occurs. Note that even when the intention is to save or write, the data mem may still try to fetch its value and output some data at the read data port. Here, we add the data mem to our data path with the address coming from the ALU and data in coming from read data 2, as the source register for store words must be RT. We will also need a new control signal, write mem, to be asserted only when writing for store words. However, now we'll have to support two sources of data for writing into the reg file. Thus, we added a new multiplexer to support write data coming from the ALU for add sub, and or, and add I instructions, and also write data coming from the data memory when executing load words. Accompanying this new multiplexer is a new control signal, cell data, which, following the connections shown, must be asserted when executing load words. To demonstrate how a load work will work in our data path, consider the load word instruction shown stored at 0x30. The operation starts from the PC, feeding the instruction address to the inst mem, which outputs the load word instruction. From the instruction code, RS and RT can be extracted. Note that RT will be used as the destination, so cell dest must be set to 0, while RD can be considered as a don't care. At the same time, the adder computes and prepares the PC plus 4 at the input of the PC register, and the reg file outputs the contents of R4 and some don't care data, which is actually the contents of register 22. The immediate will also be sign extended and fed to the ALU by setting cell of B to 1. After some delay, the ALU will output the effective address and fed to the data mem. The data mem will also receive some don't care data from readreg2, which we will not use since write mem is deasserted for load word instructions. The memory will be able to output the contents of the memory at address R4 plus 4 and feed to the register file with the select data having a value of 1. At the same time, the reg file receives an asserted write RF signal. Thus, when the rising edge of the clock occurs, the load word instruction must be completed. Now let's consider a store word example. In this example, the instruction is fetched from 0x34 and RS and RT values of 4 and 23 are fed to the register file. Note that this time, the RT value is essential as it will be the source of the data to be written to the data memory. The address is computed from the immediate, which is -4, which is sign extended and added to the contents of R4 by the ALU. This address is fed to the data mem, and the write memory signal is asserted to be able to write into the data memory. Note that we are not writing into the register file, so the write RF signal must be deasserted, and with that, the write reg value is a don't care. Similarly, whatever is being fetched from the data memory at this specified address is a don't care, as well as whatever is being fed as the write data input to the reg file is a don't care as well, since again write RF is deasserted. Okay, we currently have a data path that can support 7 different kinds of instructions. So that's 4 for rtype and add-I, load word, and store word. Let's now look on the control signal values that we need so far. We included some notes above to guide us in filling this control signal table. Starting from cell of B, we need the immediate value for add-I, for load word and store word, so we need these values. So 1 for add-I, load word, and immediate, but 0 for rtype. For ALU op, we always add for add-I, load word, and store word. We add for load word and store word to be able to compute the effective address. So we write that as add. However, for rtype instructions, the ALU operation actually depends on the instruction depending on the func field. So we can simply write that as a function of the func field. We will skip the two control signals first and focus on the write enable signals. Our type, add-I, and load word instructions write into the register file. So we write 1 for their write RF values. However, store word instructions don't write into the register file but write into the data memory instead. Now from this, we note that every time we don't write into the register file, we don't care what is being fed at the right ports of the register file. So we write don't care at this row. For the rest, we use the data from the ALU output as the write data for our type instructions and for add-I instructions as well. However, for load word instructions, the data that must be written to the register file must come from the data memory. Lastly, for R-type instructions, the destination is RD, whereas for add-I and load word instructions, the destination must be RT. So summarizing, this is how the control signals should look for these instructions we have so far. Also note that the values highly depend on how the multiplexers are connected. So if we interchange the connection for the multiplexers, then these values should also change. The next two instructions we will support and add in our data path are the BEQ and BNE instructions. The RS and RT registers in BEQ and BNE instructions are the two registers whose values are to be compared as a basis if we are to branch or not. The 16-bit immediate contains the instruction offset, not some address offset, since encoding an address offset will force the last two bits to be always 0, wasting bit fields. Again, the immediate is not an actual address but an offset, so branch target addresses are computed relatively. The target address is equal to PC plus 4 plus instruction offset times 4. Since the offset is added to PC plus 4 and not simply PC, this means that the counting of the offset starts from the next instruction. For example, if we have the code here, then what should be the offset for the BEQ instruction? We are to count from the add instruction below it up to the target address. That is 2 instructions forward. And therefore, the instruction offset for the BEQ instruction must be positive 2. For the BNE instruction, we have again to count from the next instruction below it. This time, the target address is 3 instructions away and backwards. So the instruction offset for the BNE instruction must be negative 3. Going back to the address computation, this means that aside from the sign extending the offset, the hardware must also now be able to multiply the immediate by 4. The new blocks added to support BEQ and BNE instructions are on the left, a shift left by 2 block which performs multiplication by 4, another adder, and another multiplexer to select between PC plus 4 and the branch target address. A new control signal for the MUX is also added, and we labeled it as cell PC INC to denote select PC increment. We have also highlighted this portion, the 0 flag, which will be used as an indicator if the branch should be taken or not. However, instead of being an output of the control unit, the 0 flag is actually an input to the control unit. In this example, we consider a BNE instruction at address 0x18 that compares registers 12 and 0 and pointed to the label loop. The instruction offset encoded is negative 3 or 0xFFFD. The immediate negative 3 is sign extended and shifted to the left by 2 or multiplied by 4 to get negative 12. This is added to PC plus 4, which is 0x1C. So the branch target address PC plus 4 plus offset times 4 is equal to 0x10 since C is 12 and subtracting 12 from 0x1C must give us 0x10. To determine if the branch should be taken or not, the processor subtracts the two register operands and checks the zero flag. If the difference is non-zero, then the operands must not be equal. Thus, for BEQ instructions, or rather BNE instructions, we branch and select the branch target address instead of simply PC plus 4 if the zero flag is deasserted. We can therefore write cell PC increment as zero flag prime or not zero flag. Also for BNE, we are not writing into the memory nor the reg file, so the write enables must be deasserted. The control signals for the MOOCs of the write path can also be considered as don't cares. We then expect that when the clock rising edge occurs, the PC should point to the next correct instruction and no other register or memory positions must be written to. As for jumps, the jump target address is based on a 26-bit immediate and can thus jump to further instructions for the most part. The immediate is also based on the absolute address of the target instruction. Consider some address AAAA, and so on, which contains the jump instruction. The fetched jump instruction should be composed of the jump opcode 000010 and the 26-bit immediate JJJJ, JJJJ, and so on. The jump target address is generated by concatenating the first 4 bits of the PC, the 26 bits of the jump address, and 2 zeros, since the target address must be word aligned. This illustration also shows that the jump target address can be generated from simple concatenation or rewiring. Also, if we do the process backwards, the target address must be shifted to the right by 2-bit places before encoding into the instruction. One thing to note is that since the jump instructions can only encode 26 bits of immediate, it must therefore assume that the first 4 bits of the target address must be the same as those of the PC. This means that if a jump instruction is at address space 0x0010, meaning its address MSB is 0010, then it can jump to any instruction within the 0x0010 space, which is quite wide. However, it cannot jump to any address where the first 4 bits are different, even if it is near to the original address. If the compiler sees a case such as this, it can replace the jump with a combination of branch and jump instructions. To support jumps, the jump address must first be generated and then multiplexed into the PC input. A new control signal, cell jump, is also needed for the new multiplexer. Note that it is possible to just use a 4-input multiplexer with a 2-bit control signal, but in this example, the multiplexers are separated to make the role of each control signal more obvious. Our updated and final control signal table should look like this one. From our last table, we added 3 more rows for BEQ, BNE, and jump. We also added 2 new columns for select PC increment and cell jump. Notice how the entries for cell PC increment are written as logical expressions instead of zeros and ones. For branch equal, we branch if the zero flag is asserted, whereas for branch if not equal, we branch if the zero flag is not asserted. For jumps, the controller asserts cell jump if it detects the opcode for jump. This makes the cell piece increment simply a don't care since the MUX's output is not selected by the MUX nearest to the PC register. It must now be obvious that as we try to support more instructions, the more complicated both the data path and control become. Also, in any implementation, it must be defined what will happen if an unsupported instruction is fetched. The safest way to approach this is to not write anything which can corrupt some data or trigger other events, and also to inform the OS and let it handle the problem. Okay, we now know how a single cycle MIPS processor data path should look like, how it works, and we have also tabulated the control signals. But how do we generate the control signals themselves? Or how is the control unit implemented in logic? We can of course proceed by doing K-maps regardless of how large the tables become. However, suppose that for demonstration's sake, we can go with non-minimal logic expressions, then we can build logic circuits directly by looking at when the control signals are asserted or deasserted. Consider this example where we are tasked to come up with a logic expression for the cell jump control signal. Cell jump signal, which must be asserted only when the instruction is a jump, which we can identify based on the opcode, which is 000010 or 2. We can rephrase this as cell jump is 1 if the opcode is 000010, or in a bit more detail, cell jump must be 1 if the 0th bit is 0 and the first bit is 1 and the second bit is 0 and the third bit is 0 and the fourth bit is 0 and the fifth bit is 0. With this, we can draw this simple logic circuit that is consistent with our intended behavior for the cell jump control signal. We can also follow the same approach for other control signals, although there might be some other logic or changes when the control signal must be asserted or deasserted for 2 or more instructions. In this example, suppose the ALU follows the ALU opcodes shown to identify what operation must be done. How then can we possibly implement a control scheme to generate the necessary or correct opcode or ALU code based on the instruction? Note that not all instructions have the func and champ fields. Also, note how in the table provided, 4 bits are defined for ALU op, whereas both opcode and func are 6 bits each. To proceed, we note first how most instructions rely on addition and subtraction operations. For example, add I, load word, and store word use addition, while BEQ, BNE, and other branches use subtraction. Note also how these instructions mentioned do not have a func field and are identified only by their opcode. Thus, we can do something like this, where the ALU op is allowed to take in the codes for add and sub using a multiplexer whose select signal is based on some logic function that takes the opcode as the input. What we can do for the remaining R-type instructions is to construct another logic block which converts the function into the corresponding ALU code. We then must design the logic block for the opcode to output an ALU select signal equal to 10 when the opcode is 000000, as is the case for add, subtract, and or instructions. We will end this lecture by summarizing some observations that we must have made as we built the single cycle MIPS data path. First, the processor data path is highly dependent on the ISA. If we consider the different instruction set with a different instruction width, different number of registers, instruction formatting, etc., then the data path would have looked different except possibly the existence of the main data path blocks. Next, placing the operands consistently within fields in the instruction code makes the data path cleaner. For example, with the first and second register operands always being in RS and RT, we were able to directly write these two signals or directly wire these two signals to the reg file without the need for a multiplexer. This is one of the reasons why it is easier to start studying data paths with the MIPS architecture. There is also a certain degree of freedom in the organization or implementation of the data path. For instance, multiplexer connections can be interchanged. There is also no specific requirement on how the reg file, ALU, or memory has to be constructed internally as long as they adhere to the expectations or assumptions when the data path is constructed. It is also shown in our previous example how the control can be constructed from smaller logic blocks. Some of these control blocks may even be built in within the data path block themselves. This also simplifies the design of the main control unit. We can also have different processors having different performance using the same architecture. This is because the blocks within them, for example, the reg file, the ALU, or the memory, can have different speeds as well. The implementation technology also affects the speed of the processor. For the control unit, we make the following remarks. First, the control unit for a single cycle processor can be described as one big chunk of combinational logic. The control unit is also mostly dependent on the opcode to identify the instruction and generate the control signals. However, in some cases, the control unit will also need some result, for example, the zero flag, or other fields within the instructions, as in the case of the champ or funct for R-type instructions. The control unit becomes more complicated as more instructions are supported. K-map or logic simplification will have to be redone for every change in the data path or instruction coding. And lastly, the control unit can be done using a more readable logic for a quicker implementation and to allow a progressive and systematic approach in building the control unit. If we did K-maps when the data path was only supporting R-type instructions, the resulting logic expressions for the control signal will change as we add the add-I, load word, store word, BEQ, BNE, and BEQ instructions. The same is true for larger designs. And that's the end of this MIPS single cycle data path lecture. We hope you learned through this video. Thank you very much.